Let's get started. So, hello everyone. This is going to be a live ML platform coding session. Just making sure, can you please tell me if you can see my screen, my presentation? Okay, thank you. Okay, so this is going to be around 2 hours. I'll do a quick introduction. I'll discuss the architecture and then jump right into coding. So let me tell you a little bit about myself. So my name is Alon. I'm from Tel Aviv in Israel, and I lead the R&D team at Aporia, where we create a product for data scientists and ML engineers that want to build their own customizable ML monitoring solution in a much faster way compared to Prometheus and Grafana, for example. So previously, I've worked in the IDF as a software engineer and then a team leader, and I've been involved with machine learning and DevOps for many years. I saw a lot of people struggling with setting up their ML infrastructure, so that's how I started this workshop. Okay, so let's start. So when you have one or two data scientists in your organization, and they start not clearly audible. Let me check my microphone. Just 1 second. Just 1 second. Is it better now? Can you please let me know in the chat? Okay. Thank you. So I will continue. Thank you. Okay. So when you have one or two data scientists in your organization and they start working on new projects, you probably focus less on your ML infrastructure. But when you have more data scientists or when you start deploying models to production, then the need for proper ML infrastructure becomes crucial. And today I will show you how to build a basic ML platform by yourself. It's not going to have tons of features, but the purpose of this session is to teach you the basic principles of how to build an ML platform. So to help you follow along, just so that they send the link in chat, you can open this GitHub repo. Basically, it contains all the code that we're gonna write in this workshop, so you can check it while I'm coding. And also, if there's enough interest, then I'm gonna keep improving this open source ML platform and add more tools. So if you're interested, make sure to follow me on Twitter and LinkedIn and let me know. Okay, so so there are different needs for infrastructure across the ML pipeline. Here are some common ones. We have the data collection and versioning. Maybe you need a feature store. You probably need a way to manage your experiments. You need to think how to serve models in production, how you monitor them, etc. So maybe some of these problems are relevant to you. Maybe some of these problems are completely irrelevant to you. And maybe there are other problems that are relevant to you but are not written here. So we believe that there isn't a single way to build your ML infrastructure. It's really important that you deeply think and understand your needs and your problems, prioritize, and find the best solution for each problem. And this pipeline is, again, just an example. Your pipeline could be completely different. So today we are going to focus on the following problems, the one marked as green. So data collection, versioning, experiments management, packaging deployment, and model serving. In this session, we are going to ignore the rest of the problems. So we're going to use DVC for data versioning. We're going to use MLflow for experiments management and packaging. And we're going to build fast API-based model servers. We're going to build all of this platform on top of AWS. But in theory, you can also use Azure, Google Cloud, or any other cloud provider. It's important to note that when building your own ML platform, you should not take these tools for granted. You should evaluate alternatives. Some of them are written here, above the boxes here, because maybe they are more appropriate for your use case. But in this session, we are going to use these tools. So before jumping into the architecture and code, let me make sure we are aligned on the basic technologies that we are going to use. So I like to explain Kubernetes in the following way. It's a very simplistic explanation, but I hope it will be enough for this coding session. So let's say you have a traditional operating system like Linux or Windows or Android or iOS. Usually, the traditional operating system is installed in a single machine, a single computer, and allows you to run multiple applications on top of it. This is the traditional operating system that we are all familiar with. And in a very simplified way, Kubernetes is similar to an operating system. It runs applications on top of it, but the main distinction is that Kubernetes can run on multiple machines and not on a single machine like a traditional operating system. And this has some advantages. For example, let's say that we're running a model server on top of traditional operating system on top of one machine, on one computer. Then let's say that suddenly you get a lot of predictions. So your model server might crash because it doesn't have enough memory, for example. So in Kubernetes, the idea in Kubernetes is that you can just keep adding more machines. So when you add more machine, it means you have more resources in your Kubernetes cluster, and you can make replicas of your model server, for example. You can run it multiple times. So if one crashes, the other one is still alive and can make predictions. So this way, you can scale and make your system much more reliable. When you install an application on Ubuntu, for example, you run something like sudo apt-get install my application. When you install an application on Android phone, you go to the Play Store and download the application. So Kubernetes has multiple methods to install apps, but I think the most popular one is called Helm. So we are going to use Helm extensively in this workshop, so I can do things like Helm install MLflow. It's very similar. It's important to know, so this was just like a simplistic way to explain Kubernetes, but Kubernetes is not really an alternative to traditional operating systems. In fact, the Kubernetes agent runs on top of traditional operating systems, but at least to me, it helps understanding what's the point of Kubernetes. Also, the applications that run on top of Kubernetes are almost always Docker containers. So we're going to use the following AWS services. S3. So S3 is a file storage service, and each S3 instance is called a bucket. So in this bucket, you can have files and folders just like a disk in a traditional computer. So I can have an S3 bucket for my models, an S3 bucket for my data, etc. So this is the first service that we're going to utilize. The second service is called ECR. So ECR is a Docker container registry. So basically, we can push and pull Docker images from this registry, from this ECR service. EKS is managed Kubernetes. So we explained what's Kubernetes in the previous slide, but the idea is that AWS take care of a lot of details behind the scenes and make it pretty easy to use Kubernetes. RDS. So AWS has a lot of services, and all of them have like, I think almost all of them have 3 letters. So it can be a bit confusing, but I will keep getting back to this and explaining what each service does when I use it, so don't worry. So the next service that we're going to use is RDS. Basically, it's a managed database. Specifically, we're going to use Postgres, which is an extremely popular SQL database. And the last service that I want to mention is Route 53. So Route 53 is a DNS provider. Basically, it will allow us to route the domain. It will allow us to route the domain ml.apora.com to our ML platform. But of course, you can use any domain that you want. This is just my domain that I'm going to build the ML platform on top of it. Okay, any questions so far? Let me get back to the previous slide. Let me know if there are any questions in the chat, please. And if not, I'll continue. Yes, slides aren't moving. Okay. Let me share my screen again. Okay, can you see the AWS services slide right now? Okay, so I'm going to continue. Thank you. Okay, so let's talk about the architecture of what we're going to build, and we'll get to coding in a few minutes. Okay, so we are starting from here. So let's say that we have a data scientist that wants to start a new project, a new model. What we're going to do is to build a template for him, a template that he can easily clone. So this template will include a very simple model, and a very simple data set, and that model will be the starting point for the data scientist. So we're going to use a technology called CookieCutter, an open source library called CookieCutter for templating, and I will show you how it works later in the session. So the data scientist basically clones the template and starts training and experimenting with the model and the data. And each experiment is going to be sent to MLflow. So MLflow is an experiment management system that's going to run on top of Kubernetes. So of course, we'll need to spin up this Kubernetes as well. So MLflow is going to save the model file themselves to an S3 bucket. S3, again, is the file storage service in AWS. So we're going to have a bucket for our models. This, we will call it the artifact storage. This is basically where we're going to store all our models. For example, the model pickle or any format that we'll choose. So the data scientist experiments with the model. It sends that experiment to MLflow, and MLflow in turn saves those experiments to the artifact storage. Cool. So each version, so MLflow is going to save the models in the artifact storage, and in addition, MLflow is going to send a metadata about the experiments and metadata about the model to this SQL database, to the Postgres. So in this Postgres, we are going to have the model metadata, for example, the experiments history, metrics, etc. Additionally, each version of the dataset is going to be committed to this S3 bucket. So we're going to have a bucket for the data and a bucket for the model. And we're going to use DVC for that. So basically, this is the dev part. So we're going to have our experiments, our models tracked, and also every version of our dataset is going to be tracked. So let's look at the production part. So we're going to run our model servers on top of Kubernetes again. So in this example, we have 3 model servers. And these servers are going to load the model from MLflow. So when this server starts, for example, when the model server of model 1 starts, it will pull the model from MLflow. And MLflow is going to read the model from the artifact storage, which again is the S3 bucket that we are going to save our models in. So in this Kubernetes, we're going to have the MLflow server, and we're going to have all the model servers, a server for each model. But when you install, the problem is that when you install an application on Kubernetes, it's not exposed to the internet by default. So to expose applications in Kubernetes to the internet, we are going to use something called Traefik. Traefik is an API gateway, and it basically allows us to expose other applications that run on Kubernetes to the internet. So let's say we have this web application that wants to make a prediction. So this web application will need to create an HTTP request, an HTTP post request with the model parameters. It will be sent to Traefik. Traefik is the gateway to our ML platform, and Traefik will route to the correct model server based on the URL. So if my URL starts, for example, /model1, then it will route to the corresponding model server, which in this case will be the model 1 model server. So any questions so far? Let me look at the chat. Okay, so one question was if ECR is similar to Docker Hub. Yeah, so ECR is very similar to Docker Hub. Basically, it's like a private version of Docker Hub in AWS. Another question was if there are any alternatives to DVC. Let me show you. So DVC has a lot of alternatives. There's Pachyderm and Weights and Biases and GitLFS, and many tools overlap each other. So later on in this session, I'm going to show you a cool website that will allow you to compare between different tools. Let me see if there are any other questions. Yes, so Terrific, again, Terrific is basically the gateway to our ML platform. It allows us to expose applications that run on Kubernetes, like the model servers, to the internet. Okay, and this is our architecture. So let's continue. Okay, so usually when you set up infrastructure in the cloud, it looks like this. Well, you go to the AWS console and you open, for example, you can create a new database, and it's really complicated. You have a lot of parameters, and you can easily make mistakes. So in this session, we're going to use a concept called infrastructure as code. So the idea is that instead of defining our architecture in user interface, in complex user interface, we're going to write code. So in this example, I have this line here, this code line, which represents a Kubernetes cluster. I can also have another line, another piece of code that represents an S3 bucket, for example. In this case, it's the artifact storage. Again, it's the bucket that saves our models. So the idea is that I write this file, this code that represents my infrastructure, and then I run Pulumi app. So Pulumi is the open source tool that takes this code and spins up this infrastructure in the cloud. So instead of creating and using the user interface manually, I write everything as code. So this thing has multiple dimensions. So let's say that you are working on your infrastructure as a team. For example, you have a team of ML engineers. So each change to the infrastructure can be code reviewed, and you are less prone to mistakes. Additionally, you can easily share infrastructure components. For example, I can write code that installs MLflow, and then just send the source code of this component to my friend. And I believe that this is very strong for the MLOps world. In the MLOps world, you have so many tools, but this technique allows you to quickly iterate and play with different tools. So just to clarify it a little bit better, so the first time that I run Pulumi app on this file, it will spin up a new Kubernetes cluster, a new S3 bucket. If I run Pulumi app again, then basically it won't do anything because the state in the code is the same as what I currently have in AWS. If, for example, I comment out these three lines of code, the S3 bucket, then Pulumi won't touch the Kubernetes cluster because it's still in the code, but it will delete the S3 bucket from the cloud. Okay, so this is the idea. The idea is that every time that you run Pulumi app, it basically compares the code to what you have, to what you currently have in your cloud, and then make the necessary changes. So there is another very popular tool for infrastructure as code. It's called Terraform. So Pulumi and Terraform are kind of like two competitors. They're two products that do very similar things. But I choose Pulumi because it allows me to define my infrastructure in a real programming language. So you can define your infrastructure in Python, in JavaScript, in TypeScript, in many other languages. And in this session, I chose to write my infrastructure in TypeScript. And maybe later on, I can explain why. OK, so let's get started. So this is a real live coding session. So there might be some bugs that we'll need to investigate in real time. But that's part of the fun. And we're going to cover a lot of details really, really fast. So if you don't understand something, don't worry about it too much. And the high-level picture is much more important. And again, let me know in the chat if there are any questions. And I will, actually, let me take a look if there are any questions right now. OK, so one question was if Terrific is comparable to Nginx. Yeah, it's very similar, but Terrific is more appropriate for Kubernetes. Terrific is, yeah, everything that we're using is open source. So this was another question. And I'm going to continue. OK, so let me share my screen again, just 1 second. Just 1 second. Okay. So can you please let me know in the chat that you can see my screen? Okay, thank you. Okay, so the first thing that we're going to do is to basically spin up this Kubernetes cluster and this RDS database. The reason I chose to start with those two is because it can take around 20 minutes for them to go live. So I want to basically to write the code that starts this the Kubernetes cluster and the RDS database. And later on, we will continue working and adding more things, and this will just make sure that we won't get stuck later on. So I've prepared 2 GitHub repos. The first one is called ML Infra, and the second one is called Model Template. So ML Infra is basically going to have the Pulumi code for all of the shared infrastructure of our ML platform. So for example, it's going to create the Kubernetes cluster and those S3 buckets and this database and run and also spin up MLflow. So MLflow is shared to all our models. Therefore, its place is in the ML Infra repo. The second repo is called Model Template. So Model Template is basically the template that data scientists clone when they want to start a new project. Okay, so let's start by just 1 second. Okay, so let's start by cloning the ML Infra repo. So I'm gonna just do git clone, and the first thing that I want to do is to create a Kubernetes cluster. So, okay, so the first thing that I want to do is to create a new Pulumi project. So I'm gonna run Pulumi new. So this is the CLI of Pulumi. Basically, it allows us to do operations related to Pulumi. And I'm going to choose AWS TypeScript. I'm going to write my Pulumi code in TypeScript, and I'm going to use AWS. So this is going to be the shared infrastructure for our ML platform. We'll just go with the default values here. But we will use this region. And now, basically, this CLI install dependencies related to Pulumi. It's just going to take 1 second. And then we'll open this in Visual Studio Code and start coding. So just 1 second. Let me see if there are any questions so far. Yes, so one question was if I can share the GitHub repo link. So yeah, I've just sent it. You can check it in the Zoom chat. Okay, so say it takes some time. Let me just start with this code right here and let this finish. Okay. Okay, so this is how Pulumi code looks like. I'm gonna remove these default values here. Okay, so the first thing that we want to do is to create a new Kubernetes, cluster. So the way to do things on Pulumi is just basically to Google them. So let me just Google AWS Pulumi Kubernetes. So I'm just gonna go to the first link here, and I'm just gonna copy the code. Okay, so let's write a comment here. Let's create a Kubernetes cluster. We will call it ML cluster. And basically, Pulumi allows us to expose variables. We'll see later how to use it. But we will need to install these dependencies. So to install dependencies in TypeScript, we do something like this, npm install, and then dependency name. Okay, so if I get back to the architecture, so basically this should, after I'm going to run Pulumi up, this should spin up this Kubernetes cluster. Okay, So the second thing that I want to create is this model metadata database that MLflow will later use. The reason I start with those two, again, is because these are the things that take the most time, so I want to get them earlier live. Okay, so again, I'm gonna Google now Pulumi AWS PostgreSQL, for example. I'm just gonna click this link here and just copy the code. So everything has example code. Let's join and copy the code. Yes, so let's write a comment here. We want to create a Postgres database for MLflow model metadata. And we will call this MLflow DB. We use 32 gigabytes of storage. The engine is Postgres. The version will use this version and this instance class. We'll call the database MLflow. We don't need this parameter here. And the username is going to be Postgres. And the password, so this is the password, but we obviously want a more secure password because the Foobar is not such a secure password. So what I could do here is something like this. If I just used TypeScript random function, then it won't work so well. The reason is because every time that you run Pulumi app, then it runs this code, okay? And then it compares the resources that you created in this code to what you actually have on AWS. So I can't use random here because each time that I run Pulumi app, it will create a new random password. And this is obviously not what we want. We want a single random password. So I'm just gonna Google Pulumi random password. I'm just gonna copy the example here. So this requires another dependency. We'll start in a second. Okay, so this is so this is the MLflow DB password. Let's call this the MLflow DB. So we want a password with 16 characters and no special characters. It's MLflow password, and now we can use this. This is just like any other resource. Okay, so before running Pulumi app, I just need to make sure that that this database is accessible by this cluster. So the way to do it is to use a concept in AWS called security groups. So if you're not familiar with security groups in AWS, don't worry about it too much. You can just Google it later. But we want to make sure that our EKS cluster is accessible to this RDS instance. So again, EKS is managed Kubernetes on AWS, and RDS is managed database. In this case, Postgres. So okay, so we want to use the following security group. This should be cluster security group. And we also have node security group. Okay, so again, if this doesn't if this is a little bit complex, you can just read about security groups later in the session. We also need another parameter called create OIDC provider true. So I will explain in a few minutes why we need this. But again, the idea is this. So we have a Kubernetes cluster. We generate a random password for the MLflow database. And then we create that database using this password. So we also need to install this dependency, and then we're gonna run Pulumi app. Okay, let me just see that it's finished here. Good. Okay, good. So let's run Pulumi app. This should read this code, read the resources that we wrote in this code, and create this Kubernetes cluster and this Postgres database. Okay, so I'm going to run Pulumi app, and check if there are any questions. Okay, so I see. Okay, so about the mlinfra.git. So mlinfra, the mlinfra repo is actually private, but I open source the code in a different repo. It's called ML Platform Workshops. So just Google for that. Okay, so this will take around 15 to 20 minutes, and in the meanwhile, we'll keep working. So let me get back to the architecture. Okay, so right now we are creating the EKS, the Kubernetes cluster, and we're creating the RDS, the Postgres database for the model metadata. So the next thing that we want to do is to install MLflow on top of this cluster. So before we're installing MLflow, we already created the model metadata database. But now we need to create this artifact storage, this S3 bucket that will store all of our models. So let me Google Pulumi S3 bucket. And again, just everything is Googleable, so it's really easy. And then you can just copy the example code, just like we did the Kubernetes and RDS. We want to create an S3 bucket for the artifact storage. So we don't need all those tags. We can call this artifact storage. And we will need read-write permissions because we're going to write models to this bucket and we're going to read models from this bucket. So it's going to be public read-write. Okay. So this should, the next time that I'm going to run Pulumi app, this should create an S3 bucket. So let's get back to the architecture. So we have this model metadata database, we have the artifact storage, and now we can actually install MLflow. So let me just do a quick recap. So when the data scientist experiments and play with the model, then the model, the experiment is going to be sent to MLflow. And then MLflow is going to save the artifact, the model itself, and metadata about it in this S3 bucket and this RDS database. So now we're going to install MLflow on top of the Kubernetes that we created. Actually, still creating. Let's see that everything is OK right now. Yeah, so it's going to take some time. OK, so as I mentioned before, let me get back a few slides. So to install applications on Ubuntu, you run something like apt-get install my applications. To install applications on your Android phone, you go to the Play Store and download your game. But on Kubernetes, what we're going to do is to use Helm. So let me show you how it works. So I'm going to Google MLflow, Helm. I'm going to click here and install. And yeah, basically that's how you can install MLflow on a Kubernetes cluster. So you do something like this, Helm install, you give it some name, and then MLflow, and basically this is the URL to download MLflow from. So we could actually run this in command line, but we want that everything, all of our infrastructure, we want everything to be managed in code, because this gives us all the advantages of infrastructure as code. For example, if I add a new tool, then my co-workers, my teammates can code review that and make sure that everything is OK. So I'm going to use Pulumi to install that Helm chart. So let me Google Pulumi Helm chart. Just like we Googled Pulumi Kubernetes and Pulumi RDS, I'm going to Google this. And I'm going to just copy the code. Copy the code. Let me move that import to here. And we will need to install this dependency. So just so I won't forget, npm install Pulumi Kubernetes. OK. So what we want to do right now is to install MLflow. So let's call this resource MLflow. So basically every resource in Pulumi, the first parameter is always is always the name of the resource. It's just a name that you can give it, any name that you want. For example, here we used ML4DB, here we used ML cluster, just any plain text name that you want. Okay, so the chart name is gonna be MLflow. Chart is basically like an Helm application, a Kubernetes application. And we need to give it the URL to download it from, which is this. So let's copy that. Okay, we don't want this version here. And we want to make sure that this Helm chart is going to be installed on the Kubernetes that we're creating right here. So the way to do this in Pulumi, and you can read it in the docs later, is something like this: provider, cluster.provider. So this basically tells Pulumi to install this chart on this cluster. So in the meantime, let's see that everything is running. Okay, great. Everything looks good. Okay, so let's get back to the architecture. So basically now we are installing Helm, MLflow Helm chart on this Kubernetes, but we need to connect MLflow to the artifact storage and to the model metadata database. So Helm basically has a concept called values. So values is like the settings that you can pass to this Helm chart. So let's see what settings the MLflow Helm chart provides. Let me close this. Yeah, and okay, so usually Helm charts have like this table where you can see all of the settings. Obviously, we don't need all of those settings, but we do need to connect MLflow to the Postgres and to the S3 bucket for metadata and artifacts respectively. So in this example, they configure MLflow to talk with this Postgres database. So I'm just gonna, this is a YAML, I want to convert it to JSON, and then we can put it in Pulumi. Just gonna copy paste that. Okay, so this is basically the connection details for the Postgres, for the ML4DB Postgres. So I'm just gonna replace that with the username and the password and the host name and the port. And the database name is gonna be MLflow. Okay, so that should connect MLflow. Let me go back to the architecture. That should connect MLflow to the model metadata database. The next thing that I want to do is to connect MLflow to this artifact storage. So let's get back to the to this table here. And we have this default artifact root, which is basically it can be a remote file path to an S3 bucket. Let's copy this value, default artifact root, and we have the format of this thing is going to be something like S3 and then the name of the bucket. So the name of the bucket is basically artifact storage.bucket. So this is almost okay, but actually in Pulumi, I can just use plus, the normal plus operator, to concatenate between strings. The reason is because basically when you run Pulumi up, then this thing doesn't exist yet necessarily. Okay, it can exist in the future. So it's basically an asynchronous interface, and if you didn't understand that, don't worry about it. You can read it later in Pulumi documentation. So to concatenate string, you just need to do something like this. Name and then bucket name. So this will concatenate the name of the bucket to this S3 protocol right here. Okay, so before running Pulumi app again, we need to basically make sure that MLflow has access to this S3 bucket here. So this, by default, Kubernetes pods cannot access S3 buckets. So we need to make sure that it can. Okay, so just 1 second. Yeah, okay, so let me close some tabs here. Okay, so Kubernetes, I told you that it's not an operating system, but comparing it to an operating system can help understanding what it does. So in Kubernetes, you also have a concept called users. Okay, so I can create a user in Kubernetes that runs this MLflow server, and I can configure this user to have permission to access this S3 bucket. So this is exactly what I want to do right now. So there's this component. This is a Pulumi component that I shared. It's completely open source. So basically, a service account is just the Kubernetes name for user. So service account and user is exactly the same thing. And basically, this component defines a user in Kubernetes that can access an S3 bucket. So we are going to use this component and run MLflow using the user that we're creating with it. So let's copy that code. We'll call it S3 service account. Just copy paste here. This is, again, completely open source. By the way, I really think that the Pulumi developers should get this component into this library because it's super useful. And now we can use it. So we can actually create that component. Let me copy the usage example. So again, all of this is completely open source. So we'll call this MLflow service account, and we will need to import the component. Import S3 service account from service account. Yeah, so this we'll call it the MLflow service account. The namespace is going to be default, and we don't want this user to be read-only. We want that this user we want him to be able to write models to this S3 bucket head. So it's not read-only. And now we need to configure MLflow to run using this service account. So let's get back to MLflow settings, which I closed. So let me open it again. Yeah, and you can see in the settings table, in the values table, that we have service account.create. By default, MLflow creates its own service account. We want it to be false, and we'll give it the name of the service account that we're creating. So let's do that. Service account. So we don't want to create a new service account because we're doing it right here. And the name of this service account is basically just the name of this. Okay, let's see what's our status here. Okay, so it's a little bit confusing because the VS Code terminal is a little bit confusing this, but it looks like it's still creating the cluster. This is going to take a few more minutes. So let me take a look at questions so far. Okay, so one question was what kind of user management is allowed by this infrastructure? So basically, in this live coding session, we are not going to do user management at all, but it will be super easy to edit. So by the way, if you're really interested in user management or any other feature, just let me know later on, and we can edit. And yeah, the IDE that I'm using is VS Code. Okay, so let's go back to our architecture and do a quick recap on what we did so far. So we are going to build a template soon, but let's assume that the data scientist is working and is sending training experiments to MLflow. So MLflow is our experiments management system. It's going to write models to this artifact storage and going to write metadata about those models in the model metadata database. So this artifact storage is an S3 bucket, which we created right here. Right here. And we also created this RDS database right here. And we installed MLflow helm chart on this Kubernetes, and it connects to this artifact storage and model metadata. And now we basically want to expose this MLflow to the internet. We want to access MLflow, for example, from the data scientist local machine. So to do this, we're going to need to install Triffic. Okay, so Triffic, just like any other Kubernetes application, we're going to install it using Helm. So let me just Google Triffic Helm. And just to clarify, Terrific is a Kubernetes application that lets me expose other applications to the internet, other Kubernetes applications to the internet. So let me go to Terrific Helm. I'm gonna open this, and just this is the URL to download Terrific from. And this is the chart name. So I'm just gonna install Terrific. We're going to use this chart. It's going to be much simpler than MLflow. We don't need all those values. Let's call this Terrific. By the way, let me show you a cool VS Code trick that you can do to edit multiple values. So I can choose this and then click Control D. Okay, and now all of those three are selected, and I can edit all of them concurrently. So this is pretty useful. Okay, so the URL to download Terrific from is this. And this should basically install Terrific. Okay, so this is the Helm installation of Terrific, which we're going to use in a second to expose MLflow to the internet. Okay, so the next thing that I want to do is to expose /MLflow on Terrific. Okay, so to install, to expose something on Terrific, I wrote another component. Again, it's really useful. At Aporia, we use it a lot. It's, again, completely open source. And basically make sure that you can give it a prefix, for example, /MLflow, and the name of your application, and it will make sure to expose that application on Terrific. So let me copy that. This is going to be a Terrific route. And I'm going to import that. Terrific route from route. Cool, and now let me copy the example. Okay, so we want to expose /MLflow on prefix. So let's call this MLflow route. Everything that starts with /MLflow, we want to use the MLflow service. So the way to do it is something like this. We get this. A service is basically the Kubernetes object that allows networking. So if you're not familiar with it, you can read it later on. But this is basically tells Terrific 2 that every URL that starts with /MLflow is going to be routed to this service. And again, we're going to use the default namespace. Okay, so I just saw that it completed the first Pulumi app. Just as a reminder that our first Pulumi app has basically created this cluster and this module metadata database has just finished. So this is these pieces of code. And the next time that I'm going to run Pulumi app, this cluster is going to exist, and it's not going to do anything about it. Same for this RDS instance. But all of the code that we wrote since our last Pulumi app is going to be created. Okay, so just one more thing before we can actually see MLflow. So we need to, let me go back to the architecture. So basically, this Terrific now can actually route everything that starts with /MLflow to this application. But we still need to make sure that ml.aporia.com, which again can be any domain, is routed to this Terrific. And for that, we're going to use the Route 53. Again, like everything else in Pulumi, I just do the Pulumi Route 53 zone. So record. And by the way, this varies a lot between different kinds of domains, so don't worry about it. So we want to create the ml.aporia.com domain. Let's call it DNS record. Yeah, so the zone ID, let me copy it from AWS console. Yeah, so this is my zone ID, and we have ml.aporia.com. This is going to be a synonym. If you're not familiar with it, you can read about it later on. And now we want to make sure that it's routed to this Terrific that we installed here. So the way to do it is something like this: Terrific dot get resource. Yeah, so just like I'm getting a resource from the M chart, I can get this service, the Terrific service. So I can do something like this. And this should be .status, .load balancer, .ingress. .hostname. Again, don't worry about this part too much. It varies a lot between different domains, but that should create the ml.epora.com domain, and that should actually route to this traffic. Okay, so let me just check that I did not miss anything. Okay, so we already did this. This already exists. We created this S3 bucket. We created this MLflow service account, right? It's not read-only. And then we installed MLflow using this database and this S3 bucket. And that, and we are assigning it to the cluster, just going over things to make sure that I didn't miss anything. And then we install Terrific on the cluster and the Terrific route. Okay, that should work. So let's run Pulumi up again. This again will take a few minutes. And I'm going to take a look at questions. Okay, so one question that I see here is that why I chose Terrific and not Istio. I think you pronounce it Istio. So basically, I think Terrific is much more simple than Istio. But Istio is actually more than just an API gateway, more than just something that routes between different things. It's also a service mesh and so on. And in general, I really like to use small tools that are really focused and solve the problem that I have. So personally, I don't really like huge tools that solve everything, because I think the solution is less appropriate for the problem in most cases. Let me see if there are any other questions. Okay, so I don't see any right now, so I'm going to continue. So this basically creates the the Terrific and the DNS record and installs MLflow and all that. I hope that there aren't any errors, and we'll get to this in a few minutes. Okay, so let's get back to the architecture. So we installed MLflow, we created a Kubernetes cluster, and MLflow runs in that Kubernetes cluster. We have this artifact storage and model metadata. So we are actually ready to start building our model template. So this is the second repo. The first repo was MLinfra with the shared infrastructure for our ML platform. So the second repo is going to be the template that data scientists can clone and use it to build their own projects. So for the model template, I'm going to use a tool called Poetry. Poetry is really cool, but I'm not looking for poems. I'm looking for Poetry Python. Okay. Yeah, so Poetry is basically, you are all familiar, I assume you're all familiar with Python pip, PyPy. So Poetry is basically is a tool that helps you set up virtual environments and manage your dependencies in a really easy way. So let me show you how it works. So I'm going to create a Poetry package for my model template. And then, for example, I can run something like Poetry add and a specific package. And this will create a shared file, and then I can just publish it and build it and send it to my friend, and he can install those dependencies again. So let me show you exactly how it looks like. So let's clone the model template repo. I'll do this in a different tab. Okay, so cloning the model template repo. Okay, let's open it in VS Code. So it's currently empty. And let's start a new Poetry package. So we'll call this, to start a new Poetry package, we're going to run Poetry new. SOC, and we're going to call this my model. So this is going to be the template, but later on, we're going to use my model everywhere, but later on, we'll switch it to a template variable. So data scientists can write, for example, fraud detection, and then all the code that is generated for him will use the term fraud detection. Okay, so I'm going to run this. And this just created a basic Python package. So we have the SRC directory, and we have some empty tests, and we have this PyProject file. So this PyProject file basically represents the package and all of its dependencies. So let me add a lot of dependency. I'm just going to copy paste that because it can take some time. I need to cd to that. Yeah, so this installs all the dependencies that we need. There's pandas and LightGBM and MLflow and FastAPI. We'll explain every dependency later. But in this file right now, we can see all of the dependencies. If now my friend just clones this repo and runs something like Poetry install, then it automatically creates a Python virtual environment and install all of these dependencies on that virtual environment. Okay, so I'm going to create a training package, which is here. We're going to have the code to train our model, and we're going to have a serving package. And every Python package needs this init.py file. Yeah, so this usually varies between different organizations. So I can, so this structure is just for the current ML platform session, but when doing this in your organization, you really should think like what structure fits, like is the best for you. Okay, so let's see if our Pulumi app has finished. Okay, so this basically installed Terrific and MLflow and all that stuff. And now we can check if it works. I really hope it's going to work. Let me run ml.power.com/MLflow. Let's see. Okay, looks good, looks good. Okay, so we have MLflow running. This is pretty cool. So let's do a quick recap. So we have this MLflow server running on top of Kubernetes. This MLflow server is connected to this artifact storage and this model metadata database. And it's exposed using Terrific, so it's pretty cool. Yeah, and now we are starting the model template. And let's copy a really simple model. By the way, this infrastructure can work for any kind of library that you want, TensorFlow, PyTorch, Keras, whatever you want. We're going to use just a very simple IGBM model. It's based on the Iris dataset. If you're not familiar with it, it's really simple. Basically, it's a flower classifier. So you have 4 parameters, the width and length of 2 of the flower parts, like the sepal and the petal. And it classifies, according to these parameters, the type of the flower. Okay, so let's copy the data set to our template. So this is just a sample data set. So we are copying it as is right now. But later on, we are going to use DVC to manage our data sets. So this is just for now. Okay, so this is the data set, and let's copy the training code, which is really simple training code. Yeah, so basically all it does is to read this CSV file and then train a really simple IGBM model, nothing special. Okay, so let's just run and can see that it works. So Poetry actually gives me really cool utility that helps me define common scripts that I run a lot. So the way it works is like this. I can copy this script, and we are going to define a new important script called train. We're going to use it a lot, obviously. And it's going to run src.mymodel.training.train, and we want to run the main function. So main function. Okay. So let's just make sure that the training code works. So I'm going to run Poetry run train. So this is the script that we defined right here. Let's just make sure that everything is loaded correctly. Okay, and these are some LightGBM warnings. I'm gonna completely ignore them. Okay, so the first thing that I want to do is to integrate MLflow into this training code, into this simple LightGBM training code. Okay, so I'm gonna import MLflow.lightgbm. And the first thing that I want to do is to enable auto logging. So MLflow basically has functionality to automatically see that you're training the model and predicting, etc. And it will report those to MLflow. So login. So we have our tracking URL. The URL of our MLflow server is gonna be this thing that we just saw. Okay. And we're gonna write autolog, which will automatically logs all the things that it can. Okay, so the next thing that I need to do is when training my model is to do something like this, MLflow.start run. And basically, in MLflow, a run is an object that represents each each execution of the training code. So this is a run, and I can print the run ID. The run ID to the console. We will need this later on. So this should be run.info.runid, I think. Let me check. Yeah, run.info. Okay. And by the way, in MLflow, you can also, for example, log custom metrics. So you should really take a look at MLflow documentation. It's pretty cool. I could do something like this: log metrics, log loss, for example, and metrics. Okay, so let's run this again. This will take a few more seconds. But now, after running this, we should see this experiment in MLflow. So let's make sure that's working. Let me see if there were any errors. Not yet. So if I go here, okay, cool. So I can already see that an experiment has started. It's not finished yet because this hasn't finished yet. Okay, so we finished. We have a run ID. And if I refresh here, then okay, so it's finished. And now in MLflow, I can actually download, for example, the artifact. So this is the model itself. And this thing sits on the S3 bucket that we created using Pulumi. So it's pretty cool. Okay, so let me see if there are any questions. Okay, so one question was if this runs locally or remotely. So everything, yeah, so the training code runs locally, but the Kubernetes runs on AWS. Okay, so we created the Kubernetes cluster on AWS using Pulumi. Another question was how do I enable HTTPS for MLflow? So in Terrific, you can do all that. It's really simple. You can just Google Terrific HTTPS and you can basically enable HTTPS for some domains, for some routes, and for some you don't have to enable it. So just Google that. It's pretty cool. Let me see if there are any other questions. Okay, I see a question about advantages of poetry versus Pyend, and I see that someone answered that. Okay, so let's continue. Okay, so we started working on this template, and we have training code that currently sends the model to MLflow. So we can see the model right here. Cool. Okay, so the next thing that we want to do is to start working on the Fast API server. We want to start working on the model server, on the HTTP server that is going to serve our models. So let's do it in the serving directory. So let's call this main.py, and let's just Google for some HTTP Fast API example. Fast API example. Let's just Google that. Let's just copy paste. Cool. Okay, so just to make sure that it will run, I have to do something like this. So basically, I'm going to use Uvicorn. Uvicorn is just a library for running servers like Fast API in a really fast way. So because I want to debug, then I'm just going to run UV.run. This is just for debugging. So yeah. Okay, cool. So this should run our fast API servers. Currently, it doesn't have anything. So let's just make sure that it works. But actually, I want to add another useful script. We had train, and we could use it to run, for example, poetry run train. So we're gonna use, we're gonna add another script called serve. So it's gonna be serving the main, right? So serving main, and we're gonna call the main function. Okay, so let's check if it's working. Poetry run serve. Okay, we have a simple HTTP server running. Let's see if we can browse to that. Localhost. Okay, cool. So we get this hello world message, and we can start working. Okay, so the first thing that we want to do, let's go back to our architecture. Actually, are there any questions so far? If you have any questions, please type them in the chat. So just make sure that everything is clear. Okay, so one question that I see is, MLflow has model serving capability. How does that compare to this approach? Okay, so if I go back a little bit to our, in our slides, let me just, yeah, okay. So in an ML platform, you have all sorts of parts. You have the serving part, and you have, so in different tools have like overlaps. Okay, so I could use MLflow for model serving. I could also use MLflow. I could also use DVC for experiments management in a way. So there are a lot of tools, and not only that, there's a lot of tools. It's also there's a lot of overlap between those tools. So this goes back to this point that it's really important to understand the tools and to understand your problems and to choose the best tool for each problem. So I didn't want to use MLflow for serving because it's less customizable in my opinion, but maybe it's great in your application. So by the way, I just want to show you a cool website that we created. It's called MLOps Toys. It's completely open source. You can contribute in GitHub, and I can filter by category, and I can see different tools for different categories. So these are all model serving tools. So we have BentoML and Bodywork and Kef serving and Seldon and many tools. And it's pretty cool. You can see for each tool what it works well with AWS Lambda, and it competes with this tool. So this website can help you choose between different tools. And additionally, to understand the solution in the best way, in my opinion, one of the best ways to do it is to play with it. Okay, is to just start local Kubernetes, local environment, like in 2 or 3 hours, just like we're doing in this live coding session. You can set up, for example, Kubeflow and check if it's good for you. So I hope that answered the question. Okay, so another question was, where is ECR being used? We'll use it in a second. Okay, so let's continue. Okay, so let's do a quick recap. We're currently writing the fast API servers, the model servers. And the first thing that we need to do is to load the model from MLflow, which will read it from this S3 bucket. So let's go back to the code, and the first thing that we want to do is to load the model. So let's do it. Import MLflow, and let's also import MLflow. Okay, that's enough actually. And let's load the model. So MLflow.lightgbm.load model. And here we need to get the path of the model. So if we go back to our MLflow dashboard, let's load this run ID always, but in a few minutes we'll make it dynamic. Okay, so let me clarify what I meant here. So this actually loads this model from this path. So it will call MLflow and read that model from the S3 bucket. But the problem here is this is const. This is like it will always run, it will always load this specific run, but in a few minutes we'll make it an app. So this should load the model, and this is a normal IGBM object. Okay, so the next thing that we want to do is to make an actual prediction. So if I take a look on the data set, where was it? Here, okay. So the way that it works is that we get the size of each flower part, and the model predicts the type of this flower part. So let's see how you get a request body in MLflow. So in FastAPI, sorry. So right now we want to get the parameters for the model. So let's just copy the example here. This is how you get a request, like how you get the parameters in your request body. I'm just going to copy that. And this, okay, so we want to have something like this. So this is the prediction request. We have the petal and the sepal. These are the two flower parts. I'll just fill that in a second. And for each flower part, we need the width and the length. So again, this obviously depends on your model, but this is just a quick example. So this is a float. This is also a float. So basically, we're going to get a JSON. A JSON that looks like this. Let me show you the architecture. So we have a JSON with two fields, sorry, saddle and petal, which are the two flower parts. And for each one of them, we have width and length. Okay. So now we want to make it so that when every time there's an HTTP request to /predict, it will make that prediction. So let's do that. So every time there's an HTTP post request to /predict, let's call this predict. We want to get the request body, which is this. And now we want to make a prediction. So first step here will be to pre-process. So we will create a data frame. We will do that in just a second. The second step is to predict, and the third step is to return the prediction as response. Okay, so this is just a quick overview of what we're doing. Okay, so let's import pandas. And let's create a data frame with single row, okay? The one row for this flower. Data frame. Each data frame has columns and data. And we're going to have one row. So I'm just going to open this array right here. Okay, so the features for this model are, let's copy them from the training code. These are the features for this model. And we need to fill them from the HTTP body request. So we have request.paper.length. And we have also the width. And we also have the same thing for the paper. So again, this is just a really simple example for prediction. Okay. So the next thing that I want to do is actually to make a prediction. So we have model.predict. Again, this is just a normal IGBM object that MLflow loaded from the S3 bucket. We want to predict that data frame. So now this will return a probability, an array of probabilities. So we want to take the best class. So we're going to use argmax. Argmax. This is going to be the best class, and we need to convert that to an integer. And now we can finally return the flower. Okay, so this will return the number of the flower, but we could also post-process and get the actual name, but it doesn't really matter. So this is the actual prediction. And let's check if it works. Okay, so I'm going to run this thing again. I'm going to run the server again locally. We will deploy it to Kubernetes in a second, but I'm going to run it locally again. But before running it locally, I need to make sure that it can communicate with my MLflow instance. Let's copy the URL, and we need MLflow to be this. Okay, let's run the server. And it should, let's see what it should do. Okay, so it should load this model. And then we're gonna call /predict, and then we should see like this result right here. So that's it. Okay, so it looks like it's working. Let's do a quick prediction. Okay, so I want an HTTP post. It should be JSON. Okay, so our URL should be localhost predict, and this should be, for example, say something like that. And we also have the second flow part on a petal. Let's hope that it works. Oh, sorry, not height, should be length. We have an error. Predict request object has no attribute. I promise there will be bugs. Let's see. Oh, I wrote petal twice. Okay, let's run this again. And in the meantime, I will see if there are any questions. Okay, so what's the difference between Pydantic and just standard Python data classes? Yeah, so I think Pydantic is really good for translating between JSON to those objects. Another question was, don't you need to set MLflow tracking URL, or does that not matter because this is running locally? Yes, so I do need to set MLflow tracking URL. I did this here locally. But when I'm going to deploy this to Kubernetes, then I'm going to make sure that this environment variable is available to that container. Okay, so let's see if it's working. Yeah, so we have insomnia. Okay, and we have a prediction. So basically, this thing loads the model from an S3 bucket. Let's do the recap. So we have a local fast API server that loads the model from MLflow, which reads the model from the S3 bucket and makes a prediction using that model. Okay. The next thing that we want to do is to deploy this server to this Kubernetes. So I'm gonna, first of all, I'm gonna make a container from this model template. I'm gonna create a Docker file. And let me copy paste that part. Just 1 second. I wrote here again, it's completely open source and it's really common. Let me explain what I'm copying. Okay, so we are using the basic Python package. We are listening on port 80. We're installing some system dependencies. Then we are installing the project dependencies. This is how you can install project dependencies using Portfree. I think there's also a Docker image for Portfree, but I'm just using this. And then we are running the UVCron server. UVCron is just the thing that's running our model server, our fast API server. So this should be actually the main. Okay, so this is running my model.serving.main. Okay, so this is a Docker container that runs my model. Also, another thing that I need to do is to make this run ID dynamic. I don't want it to be static, obviously. So let me just take that from an environment variable. So I'm going to just call it MLflow run ID. I will need to import OS. Okay, so we'll need to make sure that when we deploy our Kubernetes application, we need to make sure that we have the MLflow run ID and the MLflow tracking URL. So if you didn't understand that, don't worry about it. It will get clear in a second. Okay, so we have, so we have two repos, right? We have the MLinfra repo and we have the model template repo. And the MLinfra repo has Pulumi code for our shared infrastructure, for our Kubernetes and S3 and all that. But we're also going to have Pulumi code in this in the model template. So this Pulumi code, which is specific to a model, is going to deploy that model to the Kubernetes. Okay, so let's do that. So let's create a new infrastructure directory. again, this infrastructure is model-specific infrastructure. We have two Pulumis, one for the shared infrastructure, which is the other repo, and which is all the code that we wrote here, right? All this code, which is the Triffic and database and so forth. And we're going to, now we are creating a new Pulumi project, which is specific to the model, okay? So I hope this is clear. Let me know in the chat if this is not clear. I see two questions right now. The first question is, haven't you covered the DVC yet? So the answer is that I did not. I will get to it in a few minutes after deploying the model to Kubernetes. The second question is, why do we need to package our training and serving code with Poetry rather than running directly from the Docker file as required? The Docker, so when developing locally, Docker it's a bit slow, and so I think that when developing locally, Poetry is really good, and when you're sharing the model between team members and all that, it's automatic. Like, you don't want to run Docker each time that you change something in your serving code, right? So you can just run Poetry run. It automatically takes care of the virtual environment and dependencies and all that. Another question that I see, it seems dangerous to share ML4 for both dev and production. Do you recommend running two ML4s, one for dev and one for production? I recommend, in fact, I recommend doing one MLflow, but with different authorization policies. Unfortunately, I won't have time to cover it in this session, but definitely let me know later and I can explain how to do it. By the way, another thing that we are not covering in this session is how to make multiple environments. For example, production, staging, and so forth. We only have one environment. But if you are interested about that, just let me know and we can do that for sure. Okay, drink some water. Okay, so let's start working on the model-specific infrastructure, model-specific Pulumi. So let's start by creating the new Pulumi project, Pulumi new. In this case, we're gonna just use Kubernetes TypeScript because we're running something on Kubernetes. So this should be my model infrastructure. Models infrastructure. I'm gonna use the default variable here. And I'm gonna install some dependencies in a second. But before that, like everything with Pulumi, I'm just gonna Google Pulumi deploy Kubernetes app. I just want to deploy the Docker container to Kubernetes. So I'm just gonna copy the code. It's really good, actually. Sorry, it's this VS Code. So we have the infra directory and we have the index.txt. And this is the code. Okay, so let's understand what's going on here. The first thing that we want to do is to build and push the Docker image to ECR. Okay, so we built a Docker image that can serve our model, and now we want to build and push it to ECR. So, so we're going to call this my model image, for example. It doesn't matter that much. This is the name of the repo in ECR. And we're going to build this directory. Okay, so we are currently running inside the info directory, but the Docker file sits one directory up. Okay, so this is the context of the Docker container. Okay, so the next thing that I want to do is we have a Docker image on ECR. As you can see, it was really simple. Without Pulumi, this thing can be super complicated. So in just 2 lines of code, we have our Docker image in ECR, which is pretty amazing in my opinion. So the next thing that I want to do is to run that Docker image on the Kubernetes. But the problem is that we're creating the Kubernetes in the ML infra repo, right? In this Pulumi, in the shared infrastructure Pulumi. But now we want to access it. So Pulumi provides a pretty cool function API to read outputs, to read a different project. Okay, so we have this model template project, and I'm going to use Pulumi API to read the ML infra project, the shared infrastructure. I want to take some outputs from the shared infrastructure report. So let's do that. Read ML infra shared infrastructure. I don't know, outputs. And the way to do it is I am gonna write a code and then I'm gonna explain about it. Just 1 second. Pulumi, and this should be pulumi.config. And now we have to create a stack reference, which I'm gonna explain in a second. So this should be based. Okay, so let me explain what I did here. So each Pulumi instance, Pulumi stack, has inputs and outputs. Okay, so if I'm going back to the ML infra and I'm running Pulumi config, so these are the inputs to this stack, to this Pulumi instance. So in this case, we only have one input, which is AWS region US West 2. Okay, so so these are the inputs to a Pulumi project. What are the outputs? So the outputs, I can use the export keyword in TypeScript to basically expose something to other Pulumi projects that need it. So in this case, I expose the kubeconfig. Kubeconfig is the file that lets me access the Kubernetes that I created here. Okay, so the inputs of the ML infra repo is the region, and the outputs is currently we only have this kubeconfig. So by the way, if that point wasn't so clear, just Google Pulumi outputs and Pulumi inputs, and it will get super clear in a few minutes of video. Okay, so to read the inputs for Pulumi, I can do something like that. I can initialize this config object, and then I can read this configuration value, this base stack name, which is the name of the Pulumi instance of the ML infra. Okay, so I'm going to do this in a second, and then I can reference outputs from that stack. I hope that was clear. If not, don't worry about it too much. You can just Google it later. But let's do that. Okay, so this is the infrastructure, and this is the model specific. So I want to read this kubeconfig. So I'm just going to do the stack get outputs, and the output name is kubeconfig, because that's what I did here. Okay. So now in each model, we have access to the shared Kubernetes. And now we can deploy our application to that Kubernetes. That's pretty cool. Okay, so basically this builds the pod. This builds the Kubernetes application itself. So we are exposing the HTTP port, and as I said earlier, we are going to need 2 environment variables. First one is MLflow tracking URI. I'm gonna fill it in a second, and the second one is MLflow run ID, which is the run ID that I want to serve right now. So before continuing, I'm just going to check if there are any questions. Okay, so one really good question was, is there a way to deploy the cluster with Python? And why I'm using TypeScript? So Pulumi supports both Python and TypeScript, but from our experience in Aporia, TypeScript is a little bit more stable. So we chose to use TypeScript. But you can also use Python if you want. You can try it. Pulumi and Terraform, which one is better for ML pipelines? So this is really opinionated. I personally like Pulumi, but Terraform is also really, really good. So yeah. Okay. So let's continue. So we have this tracking URL, and we have the run ID. Okay, so the run ID is also going to be an input. to the stack. Okay, and the ML for tracking URL, we're just going, it's just going to be hard coded right now, just to make it a little bit more quicker, but it shouldn't be hard coded. Okay, it should be taken from this ML infrastructure. Okay, so we created a pod, we created a deployment. So now we can actually create a service. Service is the thing in Kubernetes that can expose that to the internet. Okay, so we're creating a service. This is a service. And now we have a service. So remember, this doesn't, this is not exposed to the internet yet. And to expose it to the internet, we need to use Terrific. So let me copy that component. Again, this is, you shouldn't really copy that. You should have, a common library for your components, but just for this session, I'm copying it. So let me copy this. So we want to expose my model on Terrific. Let me copy that components, which we explained before. Okay, so everything that starts with my model, we want to make it route to the service that we created here. And this is just a provider. Okay, so this should almost work. We have one more thing that we need to do in order to make this work. So basically, remember, when we set up this ML flow, we needed to create a Kubernetes user, Kubernetes service account that will allow it to access the S3 bucket for reading and writing the model. So we need to do the same thing for the model servers. It's pretty simple. Let's just copy this code. Let's create service account for model servers. Okay, let's call this model service account, and this should be read-only, okay? Because the fast API servers don't need to write models to the S3 bucket. So in addition, I'm gonna create another S3 bucket. I'm gonna create this bucket, the DVC bucket, which I'm going to use in a few minutes. So let's do that just to make sure everything is okay. So create a bucket for DVC storage, and let's export that. So these are the outputs of Pulumi. Yeah, so let's export. So we want to export the DVC bucket URL, and this should be something like that. Okay, so I'm a little bit jumping, but this is just creating a bucket for DVC. Okay, we'll use it in a second. And the second thing that I want to export is the name of this service account, so that our models can read from the S3 bucket. So let's do that. Okay, cool. Okay, so let's run Pulumi up. This should create the DVC bucket and this service account for models. And now we can actually use that. So right here, I can do something like service account name, and we can read it from the infrastructure. So let's do that. So again, let's see. So this is the output of the user that can read models, and we want to use this user in in the fast API server. So that's all I'm doing. Output model service account name. Okay, so this makes sure that this Docker image that we pushed right here is going to run using a service account that can read models from the S3 bucket. Okay, so let me make sure that I did not miss anything. I need to install some dependencies actually. Let's make sure to install them. So AWS and AWS X. Let's go over the code. So right here we are building and pushing the Docker image to ECR. We are reading the shell infrastructure configuration, creating the Kubernetes Pulumi provider from that. We added the environment variables. It should be the to-do, should be dynamic. We're having the run ID right here, and this is the input to this Pulumi stack. And we have this service account name. Yeah, and we are creating a service and a terrific. So that should work. Okay, so let's see what's going on right here. So this is currently creating TVC bucket and our service account. In the meantime, I'm going to check if there are any questions. So let's see. Okay, how come we were able to run serving locally with MLflow without the service account? This is a really good question. So the reason that we were able to read MLflow locally is because I have my AWS user configured on my machine locally. Okay, so when I run Pulumi app, it uses my AWS credentials to create that cluster and so forth. So this is the reason that it works. But on production, on your Kubernetes cluster, it's much more secure and you have less permissions. Okay, I hope this answers the question. Let me know in the chat if it does not. Okay, another question: how to use Pulumi to tear down all AWS infra? That's actually one of the amazing parts of Pulumi. Like to create the infrastructure, I did Pulumi app, and to destroy all AWS infrastructure, I just need to do Pulumi destroy. Okay, but I am not going to do that right now because it can take some time. Okay, so cool. So we have a new model service account, and we have a new DVC bucket. We're going to use DVC in a second. Okay, so we have this Pulumi stack. And the next thing that I want to do is to create a CI/CD pipeline. So this CI/CD pipeline is going to train the model and then deploy it to production. Okay, and this can be customized a lot according to your needs. But in this case, this CI/CD pipeline is going to be really simple. We're going to use GitHub Actions for that. So, let me show you how to do it. Yeah, so we created a Docker file. I'm going to create a Makefile. Okay, so Makefile is really standard way to, to have common commands, common set of commands. So right here, I'm going to have a train command. This command is going to train the model. Okay, this command install all the dependencies that you need, the infrastructure, the pathway, all that. And the deploy command is going to deploy the model to production. Okay, so yeah, so it's going to set all those inputs. Okay, the AWS region and the base stack name and the run ID. So the run ID, it's actually going to train the model and then take the run ID from the output, the command output. Okay, so this is why I needed this line here. And there are a lot of ways to do this, okay? But this is like, I think, the simplest one that I thought of. And yeah, so you can use this Makefile outside of your CI/CD pipeline, okay? So if, for example, GitHub Action is currently, they have a downtime, which happened just last week, and you need to deploy the model urgently, you can just use this Makefile. You can just do something like make deploy, and this should deploy the model to production. And again, we can support multiple environments and so forth, but in this coding session, we're only having one environment. Okay, so this is the Makefile, and our CI/CD pipeline is very simple. It's just gonna run make deploy, okay? So I'm gonna create a GitHub directory. This is a special directory that GitHub can read. And let's create a workflows directory. And we're going to have one workflow, one CI/CD pipeline. We're going to call it deploy.yaml. And let me copy the code for that. Again, all of this is completely open source. So all this does is basically, on each push to the main branch, it installs the dependencies and then deploys the model, runs make deploy with all the necessary environment variables. that we're taking from GitHub Secrets. So again, you can do all sorts of stuff here. You can have pull requests, and you can have tests that run on each pull request, and you can have many other things. But this is like the simplest CI/CD pipeline that I can thought of to show you like how to build this thing. Okay, so let's commit everything and see if it works. I really hope it works. Let's call this initial commit. Okay, so I'm pushing it to GitHub right now. This should push to GitHub. And now let's go to our repo, our model template repo, which we're gonna convert to a template in a few seconds after we do DVC. Okay, so right here, it started the deploy CI/CD pipeline. So that's pretty cool. Okay, so it's currently installing the dependencies, and then it's going to run Pulumi, which will it's going to train the model, then run Pulumi, which will deploy the Kubernetes application to production. Okay, so in the meantime, I want to start integrating DVC. Okay, so let's go back to our architecture. Yeah, so we have this DVC storage, and each time there's a change to the data set, we want to push it not to Git, but to this DVC storage. Okay, DVC is much better than Git with handling data files, large files, or that sort of stuff. Okay, so I'm gonna use DVC in my, so let me show you what I want to do. Okay, so we have the model template, and we have this data directory, and we have currently this iris file, which is committed to Git. So I'm gonna create a new DVC repo right here. So in this data directory. So I'm gonna run DVC in it. So this will initialize DVC, and I'm using Poetry Run because I want DVC to run on my virtual environment, okay, in my virtual environment, and not in my local computer. So this way, if I send my project to my friend, he can just Poetry install, and then he has DVC in all other dependencies, which is pretty cool. So let's initialize DVC. Okay. So we initialize DVC, and now we need to add a DVC remote. Okay, so we want to make sure that all data sets are uploaded to this S3 bucket, which we created in the ML infra. Okay, we created it in the shared infrastructure, and we have this URL here. So let's do that. So we want to do Poetry Run DVC remote n. I want to do a new remote to this project. It's going to be the default remote, default place to upload datasets to. You can configure multiple. We're going to call it S3, and this is the URL of that S3 bucket that we're going to save data in. Next thing that I want to do is to add my datasets. Okay, so I'm going to run DVC add iris.csv. It's very similar to Git, by the way. So it's currently adding this. Okay, so we have an error. So the problem is that iris is currently, this file is currently tracked by Git. So I'm just going to follow the instructions to make sure that it's not tracked by Git. And now I can add it to my DVC. So as you can see, it's very simple. And we need to ignore, and we need to actually commit DVC. Okay, so the way DVC works is that instead of committing to Git this large data set, it's currently very small, but it could be huge, we are committing a really, really small file called the name of the dataset .dvc, which is just the hash of this dataset. So this file we do need to commit. Okay, cool. So we have that. So let's push the DVC. Okay, so this should push our dataset to DVC, which is pretty cool. In the meanwhile, let's see how's it going right here. Okay, so this actually already finished training the model. It's already trained the model. we have a run ID. Let's see that we can see that run ID here. So this is the GitHub runner. Okay, so this is running from GitHub Actions. And it's creating, the deployment and everything on the Kubernetes cluster. So this is going to take a few seconds. It's uploading the Docker image to ECR and then deploying that image to Kubernetes and creating a terrific route so that we will be able to access this Kubernetes. And okay, so we need to make sure that in our CI/CD pipeline, then we are pulling data. We are pulling the data from the VC. So I'm just going to do it in my Makefile. I'm just going to add a new command called the VC pull, which is just going to pull this project. I'm just going to pull this project. And then we want to make sure that before training the model and before deploying the model, we are pulling data from the VC. Yes, this is just pulling data set from the VC. Okay, so let's see if, okay, so this thing, the CI/CD pipeline is finished, and let's try to make a prediction in production. So I really hope that it works. So this is ml.epora.com / this should be my model / predict. Yes, okay, so we got a prediction from the production Kubernetes cluster, which is pretty cool. So we trained the model, we sent it to MLflow, the model was uploaded to this artifact storage, and we're tracking everything in the model metadata database, and we have this fast API server, which loads the model from the MLflow, and we're exposing this fast API server through Terrific, and now we're actually seeing a prediction request. Which is pretty cool. Okay, so yeah, so we have the VC. The last thing that I want to show you is how to make all of this project a template, okay, a real template that users can actually, that data scientists can actually clone and play with. Okay, so let me show you how Cookie Cutter works. Cutter, I'll start from an example using Quadric. Okay, so the idea is this. Right now, I have, for example, my model in my template. But I want the data scientist to be able to call the model whatever he wants, right? And this should be, for example, fraud detection. And this file should not be called, this directory should also not be called my model. It should be called fraud detection. And the URL that is automatically generated for the data scientist should be not, let's go to the Pulumi. It shouldn't be / my model. It should be / fraud detection or whatever the data scientist wrote. So Cookie Cutter is just something that lets us replace variables in file names and file content. Okay, so let's configure our variables. Yeah, so to do that, I will need to move the GitHub to this directory. Okay, so the GitHub, the CI/CD pipeline is going to be, relevant for each model. And we're going to have a new file called cookiecutter.json. So this is a required file. And we're going to copy this example here. We don't need most of this stuff. We don't need all of that. We do need version. Version is important. We say, okay, so full name, data scientist, .com. The default project name is going to be my model. And now I can take that name, which the data scientist can replace to fraud detection. I'll show you in a second how it works. And then he can, for example, then I can replace spaces with this thing. So to have a valid module name, I am going to replace spaces with that and that with that. So this is boilerplate for, for okay. Yeah, so these are the variables, and now I can, instead of having this my model directory, I can do something like that. Let me show you. I can just replace my model with, for example, this variable. So I just can rename this directory. I'm going to use the model name, of course. I'm using it here as well. So model name is this variable. Okay, so I'm going to use it here. Oh, so I can do